Okay, so that gives us a sense of what a mole is. Now we know what a mole is and how to work with the mole and work with molar mass. We can start to get back into dealing with gases and the properties of gases, because as you saw in chapter 11.4, which you looked at, the properties of a gas, the pressure, the volume, the temperature, relate to how many individual particles of gas there are. And what a mole is a measure of how many individual particles of gas there are flying around. Put more particles in, they collide more, creates more pressure. That pressure might have caused the volume to expand. If I increase the temperature and I don't want the pressure to go up, I might need to let some moles out. So even though the temperature is higher and they're moving faster, if I have fewer of the particles, they won't be creating an increase in the quantity of force or pressure that those collisions cause. Right, so the quantity of gas in moles, the number of individual particles, is a big factor on the properties of that sample of a gas. Any questions about chapter 11.4? You guys are looking at that? So I might ask you some conceptual questions about 11.4, but mathematically the quantitative questions you can solve using the ideal gas law, because the ideal gas law comes from combining the individual gas laws in section 11.4. Right, so in the individual gas laws, for Boyle's law, you're looking at the relationship between volume and pressure, and the temperature and the moles are constant. So you can only apply Boyle's law if the temperature isn't changing and the number of moles of gas isn't changing. So it's limited in what you can do with it. Charles' law, we're looking at the relationship between volume and temperature. So here, the pressure is constant and the number of moles are constant. So again, this Charles' law relationship can only be applied when the pressure isn't changing and the moles of gas aren't changing. And Avogadro's law, relationship between volume and moles, here the temperature and the pressure are constant. So again, there's limitations. Those can only be applied when certain variables are changing and certain variables are not. That's why they're not as practical. But if I combine them together and look at the overall relationship, and I rearrange this formula by dividing both sides by volume, volume will cancel out. That means NT over VP is a constant. So now I have a formula. I can write it like this, or I can rearrange and write it like this. Either way, I have a formula that relates all of the variables involved in looking at the properties of gases. And so any problem where any one or more of those variables are changing, I can plug things in and solve using the ideal gas law. R is a constant, so I just need to know the value for R, and I can use that and plug things in. Just so you know, the ideal gas law here is not always going to give you the exact correct answer. This equation is very useful because most gases will behave ideally. An ideal gas follows the kinetic molecular theory that we talked about in the beginning of chapter 11. Right? It says that there's a lot of empty space between the individual gas particles. They're moving around randomly. When they collide, they don't attract and stick together. They just bounce off one another, and that the temperature of the gas is proportional to the average kinetic energy of the particles. That is how most gases behave. So the ideal gas law is very useful. Under extreme conditions, where if we violate the kinetic molecular theory, where if we force the gas particles close together so there's not so much empty space between them, or if we slow them down really slow so they start to attract one another, then the ideal gas law won't it won't be correct. It won't give us the correct pressure if we're using it to solve for pressure or whatever. So we'll talk more about situations like that later. But for most situations, the ideal gas law is really useful. So if we're using the ideal gas law, there's lots of different possible values for R. It just depends on when we solve this equation for R, what units we plug in for pressure, what units we plug in for volume, and what units we plug in for temperature. So notice that all of these require us to plug in Kelvin for the temperature, because that's the absolute temperature scale. It's the only one, it's the only temperature unit that can't go negative. So we're not going to get a negative pressure. That doesn't make sense. Pressure is the result of things colliding and creating force. There's either some collisions creating some force or there isn't. The minimum pressure is 0. You can't have a negative pressure. So you can't have a negative temperature, right? Because you can't have a negative amount of motion. Temperature measures the average kinetic energy. So there's either something moving there or there isn't. So the minimum temperature is 0, and that's why we have to use the Kelvin scale, because it's the only scale where 0 on the scale actually represents 0 motion. So when we use the ideal gas law, we got to plug in all our temperatures have to be plugged in Kelvin, no matter what. N represents the number of moles, so we'll need to know how many moles of the substance we have if we're going to plug that in. And then the value for R will depend on what units we use for pressure and volume. Most commonly, pressure will be in atmospheres and volume will be in liters, and that's pretty much the value for R that we're going to be using. So if you're going to use this value for R, the pressure has to be plugged in atmospheres and the volume has to be plugged in liters. If you have other pressure or volume units, you have to convert them to atmospheres and liters first before you plug them in, if you're going to use this specific value for R, which is what we'll be doing when we solve problems. So if we look at some problems here in a minute. Here's one example. You might be asked, what's the volume occupied by a mole of gas under standard temperature and pressure? So standard temperature and pressure, you don't have to memorize this, but the standard temperature and pressure are 0 temperature in Celsius, or 273.15 Kelvin, and 1 atmosphere is the standard pressure. So these are the standard values for pressure and temperature. And so if we want to know what's the volume of a mole of gas under STP, then we just use the ideal gas law. Under standard conditions, the gas should be behaving ideally. It's not some weird extreme conditions. So if we want to know what 1 mole of gas, plug that in. So we can rearrange this formula. Solving for volume, that would be dividing by both sides by pressure. And then we would just plug in. Plug in the number of moles for N. Plug in the value for R. Plug in the temperature in Kelvin. Plug in the pressure in atmospheres. When we solve for the volume, we'll end up with our answer in liters, because the moles are canceling. So I don't like the way the book does this. It has it divided up here. When you divide by units, they should be on the bottom of the fraction. Makes more sense to show them down there, because then it's easier to see them canceling moles, Kelvin canceling Kelvin, atmospheres canceling atmospheres. So what I'm left with is liters. So that's why my units have liters in the end. So that would be the volume occupied by 1 mole of a gas under standard conditions. Doesn't matter what gas I'm talking about. No, it doesn't matter. That's what's nice about gases. Because the gas molecules don't have any attractions, because they're moving fast enough and they're far apart from one another, they're not going to experience any London forces or dipole-dipole or hydrogen bonding. So it doesn't matter whether I have a gas made of a kind of polar substance or a nonpolar substance. They all behave the same way, and they expand out to the same volume when I have them under certain pressure, temperature, and mole conditions. Another example here. We want to calculate the volume of a mole of gas at 25 degrees and 1 atmosphere. Almost exactly the same, so just kind of go through this quickly. If I want to calculate the volume I rearrange for volume, plug in the given information. I've got 1 mole. I highly recommend that when you do this, you include the units. It'd be really helpful for you to check your work to see the units canceling. Don't just throw the numbers in. Because if you throw the numbers in and you don't have the right units and they're not canceling properly, you won't necessarily see that and you might get the answer wrong. The units have to cancel. If I'm solving for volume, the volume units better be the only units left. Everything else better cancel. So I'll plug in R. Plug in the temperature, 25 Celsius. Got to get that to Kelvin. Plug in the pressure. So now I see the moles are canceling, Kelvin's canceling, atmosphere is canceling. I've got liters. So then I just have to plug that into my calculator. So it'll be 0.08, 206 times 298, and I get 24 liters. So really I should be given this with at least 2 sig figs, otherwise my answer is not going to really make a lot of sense. So I have 1.0 mole, 1.0 atmospheres. That would make more sense as a question that I would write. Questions about that? A joule is a unit of energy, and it turns out when you multiply pressure times volume, that equals energy. Yep, that's a good question. And in General Chemistry 2, this actually is the value for R that's used a lot because R comes in as a constant in a lot of other formulas that do involve energy, and when you want the energy to cancel, that would be the unit you would use. Here's another example. So here we have some information about CO2 being used in fire extinguishers. Part of the reason it's used is because it's more dense than air, which means that if you shoot CO2 out of a fire extinguisher, it's not going to quickly float away from the fire. It's being more dense. It should kind of hover near the fire and stay there and kind of choke the fire out so the fire doesn't get as much oxygen. So the density of air is given. So I've got 1.2 grams equal 1 liter. And I want to calculate the density of CO2. This example illustrates how important it is to, when you're dealing with different substances, keep track of the substances in your relationships and in your conversion. Because a liter of CO2 is not the same as a liter of air. When you have a unit, and that unit is measuring a specific amount of a certain substance, keep the substance with the unit so that you don't lose track of what unit is for what substance. So for air, 1 liter is 1.2 grams. I want to make sure I don't lose track of what substances I'm dealing with. This will be more important as we move forward in the semester as well. So I want to know the density of CO2 at room temperature, at 1 pressure, 1 atmosphere pressure, which is where I would roughly be if I were using CO2 as a fire extinguisher. So how do I set this up? What do I need to do? I want to calculate the density. It's telling me I want density, so what units do I want? Grams per milliliter or grams per liter. It's giving me the density of air in grams per liter. So if I want to compare the two, I probably want them to have the same units. So I might say, if you do grams per milliliter, if I've just asked you to calculate the density, you do grams per milliliter, and it's correct, that's fine. You'll get the credit. In this case, I might want to calculate how many grams of CO2 per liter of CO2 so that I can compare its density to the density of air just to show that it is more dense and how much more dense it is. So to calculate the density, I'm going to need grams and liters, so I can plug those in. If I had a sample with a certain number of grams and I know how many liters that is, plug that in, I should get the density in grams per liter. So how do I get that? What do I do? Are there any relationships? Can I use the ideal gas law? Well, the density does involve volume, and the ideal gas law does involve volume. If I want the volume of my sample of gas, so I can plug it into this density, plug it in here, then I probably want some other way to calculate the volume. So maybe I use the ideal gas law, solve it for volume. So what should I plug in for N? It doesn't tell me how many moles to use. If I had a sample of CO2 that was like 5 moles versus one that was 10 moles, would they have different densities? No, they should have the same density. If they're at the same, well, if I have more moles, then I would have a greater volume or a greater pressure. But either way, it should balance out to the same density. Right? So the density of a substance is an intensive property. It doesn't usually matter how much of the substance I have. So I can use any number of moles I want, as long as I put as long as the moles I use to calculate the volume are the same number of moles I use to calculate the grams, then they'll both be representing the same amount, and it will be fair to divide them and get the density. So just to make it convenient, let's say I just have 1 mole. I want to know what's the volume in liters if I have 1 mole of the CO2, and I want to know what's the grams if I have 1 mole of CO2. Then I can divide and get the density. So I'll multiply the mole by the value for R. Multiply by the temperature in Kelvin. Divided by the pressure. And that will tell me my volume if I had 1 mole under these conditions. So I've got 24.5 liters. So really I'm limited to 2 sig figs because of these 2 and these 2. But I want to keep an extra sig fig for now because I only want to round once at the very end. So that gives me my volume. Now I need the number of grams of CO2 that I would have in that same amount. So if I looked at 1 mole to get the volume, I need the same number of moles to get the grams. So in that quantity of gas, 1 mole of gas, how do I figure out how many grams it is? Yeah, I'd use the molar mass. Very good, from the periodic table. So CO2 has 1 carbon, that's 12.011. 2 oxygens. And that gives me 44.01 grams of CO2 per 1 mole of CO2, right? So the relationship between grams and mole for a substance comes from the periodic table. So that allows me to cancel the moles. And if I did have 1 mole of CO2, it would be 44.01 grams of CO2. Plug that in here. And I get 1.8 grams per liter. So indeed, it is significantly more dense than air. And that big difference in density and the fact that CO2 is not combustible allows it to push the oxygen away from a fire and stay there and kind of hover a little bit without rising up through the air easily, and it helps to put out the fire.